Hello, hello everyone. Welcome to episode number 32 of the Amiga assembly programming course from the book of Fabio Ciucci, who kindly gave me the permission to stream. So my thanks go to Fabio Ciucci for his generosity in letting me streaming his book. Today we're going to be stuck on this page or on this screen. This is the theory book, and we last 2 weeks ago, because last week there was no stream, 2 weeks ago we talked about the, let me show you, we talked about the condition code register, and we talked about these 5 flags, okay, bit 0 to bit 4. Today we're going to see how they are turned on or off in using CPU instructions, okay, 68,000 instructions, and what is their behavior. This part of the book, okay, because some people might think it's quite a simple one. It is not, because what we cover here is pitfalls that everybody falls in, things to keep an eye when programming the 68,000. Okay, so all these examples here, I will not finish them today. I know for a fact from yesterday, so I know I will do 8p7, and that's the maximum I will manage to do. All these are pitfalls we all fall in when we are programming the 68,000. I can tell you there are many of these that I fall in myself, where I had bugs related to these, and I'm pretty sure many of you also fell into these or into these traps. So today we will know what to keep an eye for in terms of when we are coding the 68,000. Next time we stream, next stream, which is next week, thanks bugging 1976. Next stream, we will finish this chapter, okay? We will cover something interesting though before we finish the chapter, is how we add data, GFX data, to our assembly instructions and how to use it, where instead of importing binary. Also, we'll end up, and this is quite an interesting lesson, of how to write like a bootloader for the Amiga. Actually, not a bootloader, a boot check. Okay, basically it tells us what system we are on. Okay, so if we are using an Amiga 500, we will know we're using an Amiga 500. If we are using an Amiga 600, we will know it's an Amiga 600, etc, 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 from the hardware configuration. So it's quite an interesting piece of code what we will cover. Yesterday I realized, okay, because of what happened to me in July and August, I had a house move, and all the lessons that I'm doing right now have been prepared before July. I realized that some of the things that I have taken note of, okay, might have escaped my head, okay? I mean, it's one thing, reading the book and you know, going through it, learning it, etc. And it's one thing teaching it. You need to know more things when you're teaching it. So I do apologize if I miss something. I have my notes, I will look into them, but if there's something that I might have forgotten, I do apologize ahead. There was only one thing that I forgot yesterday, but just in case, I'm apologizing from the beginning, is just in case it happens. So let's start with the book. We're going to start with lesson 8P1A, and we're going to jump to the exercises book. Most of the time, you're going to see the Amiga, okay? Very rare you're going to see the book. However, I will be switching to the book and to read my notes. So please bear with me if sometimes you will still be seeing the Amiga and I am reading my notes from the book, because I cannot have them both at the same time. That's basically it. So let's start. The first lesson that we have in front of us is quite a simple one, the first exercise, but remember, the book, we are always building on top of it. Okay, so this is why the first one might look simple, but it is our building block to tougher bugs, let's say that, because these all create bugs in our code, what we are going to cover. Okay, so the first one is we're going to see, okay, as you see here, what happens with the flag registers, okay, not registers, or with the flags in the conditional code register when we do a move instruction into a data register, okay? So I'm going to switch to the Amiga now. And we're going, so as you can see on the screen, we have our move instruction into the 0, okay? I'm going to assemble it. I'm going to do an X. This displays the registers of the CPU, X, okay? And I need to explain what you see up here. The first row is our data registers from D0 to D7. The second row is our address registers from A0 to A7. And notice A7 is our stack. And right now the stack pointer is at 041700518. Of course, hex. Then we have the stack pointer in supervisor mode, which we will not be using, okay, for now, but note that SSP means supervisor mode stack pointer. Then we have our user mode stack pointer, which is the same as A7. This is more for is here more for display, but now always know that the user stack pointer is actually A7. Then we have the SR register, the status register. And the status register is displayed in two ways. It's displayed as a number. Here we have a 16-bit number. Okay. And also as dashes. Forget what's in the middle. And these indicate the flags or the bits in the status register. We have 5 dashes here, and we will be interested only in these 5. Okay. Here we have 5 dashes, and this is the flags. Okay, so when we are executing instruction by instruction, we will see the flags changing here, and here is where I mean, also the number will change here because it's reflected as it's displayed as a number and as dashes, as I said. And here we will see things happening, and on these flags we can base decisions. Okay, this is our program counter where it is the PC, and the VBR is something we will not use or we will not care about, but it is the vector based register for the 68,000 where it is, which we won't be touching, we will not be discussing. The last line is we have the our instruction and where it is in memory and what the instruction is going to do. If we do an OK, okay, we execute that line, the move.w. Because we moved 0 into the 0, the Z flag is on. So note, we have the Z flag symbol on to indicate that the Z flag was set up and it was enabled. We can make decisions based on that. Now, as I said in the last stream, this part of the book, I wish it was done earlier, okay? So Fabio realized that he missed this part in explaining the conditional code register, okay, flags, okay, conditional code flags, or register if you call the lower 8-bit of the status register, and he decided to use the course of somebody else that helped him out. I forgot the name, and he is using his course to explain what happens to the flags when we are doing certain instructions. However, he was clever. Although he realized he has missed this part, he covered it in a way that he's showing us, okay, pitfalls that we all make in the 68,000. I need to jump to the Amiga. So we saw that the Z flag was set when we moved 0 into the 0. And just checking with the book to see if I skipped anything. Okay, the command X I explained. So as I said in the beginning, I cannot have the book and the Amiga at the same time. So please bear with me to make sure that I explained all the things that he explained in the first one. Yeah, I did that. Okay. I'm just going to jump to the book just to show something like a table that he created. Okay, I know you cannot understand this table, okay? The table that I'm highlighting, you cannot understand but he's saying how the conditional code flags get affected, okay? And what he's saying here is that the V and the C, okay, gets 0, gets, if they were set, they would be unset, so not flagged. The X doesn't get modified, okay, the X flag. The Z flag gets modified and set to 1 if the value is at 0, and the M flag, okay, is set to 1 if our value has the high bit set as 1. So it can be considered, excuse me, as a negative number. So let's see if there's anything else. Okay, so we've done this example and we're going to do the next example, which is related to the same exercise. So let's jump back to the Amiga and read the next one. Okay, I'm going to assemble it. And our instruction now is move.word, but this time is 1000 into the 0. Okay, so now we are not moving 0. Okay, so you can imagine that when I execute that instruction, the 0 flag is unset. Okay, it's not on anymore. Now, if we read the next example for the same one, okay, and we're going to do a move.word, okay, 8020 into the 0, okay. Give me a second now, because I need my notes. So we have a number which can be considered a negative number. We have move.word and the high bit is set. Okay, so if I execute it, okay, as you can see, the N flag is set. I'm switching between the book and the Amiga. So although you're seeing constantly the Amiga, I have to know what's coming next. So if we read the next example, we're still in the first example, but it has 4, let's say, source codes, whatever. So this time we're doing a move.long, okay? And we have 8020 also, but it's a move.long. So this time, if I execute this, the N flag will not be set because the number is not, I mean, the high bit of that number is not set. Okay, so it is considered to be a positive number by the CPU. I mean, signed and unsigned is a choice that we make in a way. Okay, so the CPU is always working with positive numbers. But if we are working with, if we decide to work with signed and unsigned, with signed numbers, then the CPU is giving us the choice. It's telling us if you're working with signed numbers, then the N flag is set. I believe that was example number 1 and all its code. I'm just checking. Yes. So now I'm just going to switch to the book. Now we're going to do another example. We're still in 1, but this one is called 1B. The other one was 1A. And here he's going to talk about multiply unsigned and multiply signed. Okay? And what happens when we have multiply signed and multiply unsigned. Now, let me check something before I continue with this one. Yeah, okay. So notice the first part, okay, on top we have MULS, so the multiplication is signed. And at the bottom, the blue part, the last line, is MULU, which means multiply unsigned, okay? Unsigned numbers. Also note that multiplication works on words and the result is needs to fit in a long word, okay? So that's the first thing that you need to know about multiplication. Multiplication, if you give it a long word, okay, it will still work on words. So make sure you do not do this mistake. So although we have a move.long here, okay, the CPU will still cut the high word and work on the low part of it, because it can only work on words. This tree here, okay, the move long 3, the 0, it could have been replaced with move quick, okay, 3, the 0. In the example, in the second part of the same example, he used move quick, okay, he's just showing other options here. It's not the end of the world. Also, the result is stored in the destination address, okay? So whatever we have here, that's where the result goes, and it will be stored as a long word. Note one thing, okay? Just because it's a multiplication, okay? MU multiplication unsigned and multiplication signed, they can give different results, okay? So you need to be careful what you are working with, because multiply signed treats the numbers differently than multiply unsigned. So expect different results. So let's go to the Amiga and check the first part. So the first instruction, we just move a value into the 0, and you can see that it is, when I executed it, it went into the 0, okay? We're going to do the same for the next instruction, and it should go into the 1, which you see it here. Now we're going to multiply, okay? I need my notes, just in case. We are going to multiply, okay, what we have in the 0 with the 1, and the result will be stored in the 1. Notice what's going to happen. So remember, this was a signed number, so C 0 0 0 in the 1, okay, is considered a minus, okay? It's a negative number. Because of that, okay, we Hold on. Did I execute the right one? Yeah. Ah, of course. I did an X, not a K. I was wondering. I was wondering where is the result. So, I was saying that we moved, remember we are moving signed numbers, okay? So the 0 had 3 and D1 had C000. So C is considered, okay? You're seeing it as a word here, but it's a signed number because remember it works only on words, okay? So C has got the bit 16, bit 15, sorry, on, okay? So because of that, it's a negative number. Hence, the multiplication, okay, is whatever minus C00 is times 3. And remember, from maths now, plus times plus, the answer is plus. Minus times minus, the answer is plus. Minus times plus is minus, and plus times minus is minus. So the multiplication here, okay, set the negative flag, okay? You can see that the negative flag is set and the result is in the 1 and it's a negative number, okay? The multiplication. I do not know what that value becomes as minus, but it doesn't matter. What matters is that you understand the principle of that we multiplied two words which were signed, okay, and the result was a long word with a signed number. That's the thing that you need to understand. And the negative flag was set to indicate that we have a negative result. If we execute the next one, so we put 3 again into the 0, we put the same number C00 into the 0, the 1, okay, but this time we are dealing with unsigned numbers. So when we multiply the number, okay, because both of them are positive numbers, we get the answer which is 24000. Hence we have our result as we expected. So I'm just going to go to the book for a second. And I'm going to show this table, okay, which I just said it by words, but I just want to remind you that plus times plus equals plus, minus times minus equals plus, plus times minus equals minus, and minus times plus equals minus. That, I think, is 1b. We're going to do 1c, and this time we're going to deal with division. And like multiplication, division is that we have unsigned and signed, okay? And division works the opposite of multiplication. It works on long words and gives us the result in a word, but the remainder in the low word actually of the register, and the remainder goes into the high word of the register, of the destination register. So That's another difference, okay? Multiplication works with words, division works with long words. We're going to see, I'm just checking the notes before I switch to the Amiga, but as far as I know, I said everything except the last bit. Of course, if you like gurus, you can do a division by 0 and the system will display a guru. So division by 0 is definitely going to get you a guru meditation, okay? Or at least on the 68,000. So before I jump, I'm just going to say the behavior of the flags when you have a division, okay? So the carry flag is set to 0, okay? The overflow flag is set when a result doesn't fit in our low word of the register. As you can see, and I will show this, but as you can see, move.long ff whatever long went all f's division by unsigned 2, the answer will not fit into a word. So then we have the v flag set. The 0 flag is set, of course, if the result of a division is 0. The n flag is set if the numbers are considered to be signed. And the x flag remains the same, doesn't change. So let's jump to the Amiga now and try the examples. So if we execute, assemble X, display the registers, and then K. So we move 10 into the 0. We moved, so I just need my notes. We moved 3 into the 1. Now I said 10, but that is hex, okay? So it is 16. So we are going to do 16 division by 3, okay? Which the result should be 5 and remainder 1, okay? And we should see that in the 0, okay? And as you can see, as you can see, the 0 has got the 5. Remember, the result is always in a word, and the remainder is in the high word of the destination register. So that worked perfectly well. Now, we're going to move the 200,000 into the 0. We're going to move 2 into the 1. We're going to divide, and this is signed, okay? Notice what will happen. We have an overflow and the result is not even calculated. It cannot fit. Hence why we have the V flag. To deal with such a situation, we need a different way. I mean, it's not just, you need to write a routine basically. The real answer should be 100,000, okay, but it doesn't fit in a word. So only through our own routine we can handle this. So we're going to switch back to the book. And this one is something that many of us, I think, have made this mistake, including myself, many times. Especially when you run out of data registers and you use A registers. So we're going to see the difference between moving data to a data register and moving data to an address register. Funny enough, there's a difference between them. The first thing that before I go into actually doing it, okay, I'm just trying to find out where he mentions it, just to, I think here, okay, it's here. It's not highlighted, but I highlighted it with this. When you move to an address register, you're actually doing a move A, okay? Move A instruction is different than move. The only thing is that we do not see the move A. The assembler does it from our back, and let us think that move is move, okay? But actually we are doing a move A, okay? So that's the first difference between them, between a move to a data register and to an address register. Secondly, they behave a bit differently, which I'm going to show. Just before I jump, I just want to make sure that I read all the registers. Yes. Please note that there's a typo in the book here. This should be 0, not 8,000. The first example, because this 2A, okay, is divided in 2. The first part, okay, when we simulated the first part, when you simulate it here, we are moving 0 to the 0. Then we do it again and we move 8,000. Okay, so just know that there's a typo here in the book. In fact, look, here he's explaining it with a move 0, and then he's explaining it with a move 8,000. The book, I will explain this in a minute. We're going to run the example still here, okay, till we do the 8,000. So I want to make sure that, yeah. Let's, okay. So, I expect it's J, it's K I needed to do. So we moved 0 into, move 0 into the 0. So the 0 flag is set. Okay? Hold on. Let me assemble from the beginning and start again, because I think it got confused. Let's start again from the beginning in relation to this. And let me make sure that I have the same example. Yeah. So A, X, and K. So we moved 0 into the 0, and of course the Z flag was set. Now we are going to move 8, what is it, 8 and 7 zeros into 8 0, okay, and notice what is going to happen. Okay, remember it's a move A, so the assembler is converting the move.long into move A, okay, and because it's an address register, the move is a long no matter what. And funny enough, the 68,000 ignored whatever we moved, because the flags are not affected when you move anything to the address registers. The flags do not change. Now, note also that we moved at 0, it was a move word into the 0, but into 80 we moved the dot long. Now notice the next example. So the instruction is move.word, okay? Notice it's a word, 8000 into the 0. So when I execute it, the M flag is set because that number is treated as a signed number, and 8000 means that bit 15 is set. Now we are going to do a move.long 8 and 7 zeros again into 80, and again no change because move.long is a move A and it doesn't affect the registers, the flags, sorry. What I'm going to switch to the book now. And I'm going to explain this part. And I'm going to show you, because this is in pink or whatever, and this is in yellow, okay? Notice the difference between the code here and here is that here we're moving data PC into 80, and here we're moving data PC into the 0. In this part, okay, BMI will work. In this part, 80, when we move to the number into 80, it will not work. It will just not set the flags unless, because it can happen, okay, we are moving into 80, but we had an instruction before that might have set the flag. So you need to be careful. This happened to me, okay, thinking why a branch is not working, because I did something and I ran out of data registers and I went to use the address registers, and yeah, I didn't think straight, and then the code was not behaving the way I wanted to. So be careful when you are moving data into address registers, because the flags will not behave as you expect. So we're doing to B now. And to B, he's going to talk about address registers, but what happens when we have signed numbers. And I think this one is best if I show it. I'm just, before reading my notes, to make sure that I'm not skipping anything. I think this one I need to explain. Yeah. I will explain it when we're doing the exercise. Okay, let's jump to the Amiga and I'll show you the examples. So this is the code that we are going to execute, okay? Notice that we are doing a move.long of all the f's into 80, and then a move.word of a number, okay, into 80. And notice what happens. Okay, so we moved that 8 f's into 80, and you can see that 8 f's went into 80, and it was a move.long. Notice that the N flag was set and it remained set. Okay, so it's not that something happened. We move 51A7 into 80, okay, and you can see that this time 80 has got 51A7, okay, and the N flag is still set. Okay, this is from the previous example, okay, so it's still remembering. So far so good. Just to notice, okay, that although we moved 51A7, okay, the high word, and there's a reason why I'm saying this now, the high word is populated with zeros, okay, because remember, an address register is always long. Now, let's see what happens in the next example. Oops. Sorry, I just made a mess on my desktop right now, but hopefully I will recover. Okay, so, and let's read the next example. So let's show you the code. So we are moving the same as before, all F's, and then C1A7, okay? So if we assemble it, the first one, okay, we move all F's into 80. And we have the N flag set. I said it wrongly before. The N flag was set also in the previous example. So sorry for that. The previous example, I'm just going to bring it back. I'm just realizing now that I said it wrongly. When we executed this line, the N flag was set. So the N flag was set, we moved A0. And I'm telling you this because something is going to come in the next example. So the N flag was set. Now, when we why N? Okay. Execute the next instruction, which was C1A7. Note that the address register maintained the sign of the value. It was a word that we moved into a 0, but it maintained the sign C1A7. C1A7 is considered a signed number. So when you move to an address register, it tries to maintain the sign. So C1A7 becomes FFFF C1A7. And that can catch you up. So remember, and I'm going to switch on the book now because that's why it was highlighted. Remember that when moving to an address register, it maintains the sign. Okay, if this bit is set, then they all becomes 1. If it's not set, they become 0. That's how it works. And we have seen this example here where they become all F's in the high word. Let's do lesson P3. And this is a short one. When you use the test instruction, TST, we are going to test TST for the value that we have in FF02. TST tests for the value 0 in our code. So as you can tell, we do not have 0 in data. Okay, so when we run the program, it will not be flagged. How does the flags get set when you do a TST? The flag VNC, the overflow flag and the carry flag are set to 0. The X flag is not modified. The Z flag is set to 1 if the result is 0. The N flag is set to 1 if it is a negative number, so the high bit is set. It's always like that basically for the N flag. So when we run the next example, okay, sorry, I need to switch to the Amiga. And read the next example, 31. Okay, so we see that we're going to test data. Okay, so assemble it, display the registers. Okay, you can see, because dato doesn't have a value of 0. The 0 flag is not set, but we have a negative number there. Because we have a negative number, the N flag is set. So just keep that in mind, that we also get the sign when doing a test for 0 or not. It's a very short one. So we're going to do jump to 8, 4. Let's go to the book. Okay, this one is very hard. I mean, I'm going to explain it, but it's very hard to show it, unfortunately, because you will not be seeing the values, these values down below when we are executing it. So I do apologize, but it's difficult to stream. This particular one is very difficult to stream. However, we're going to do it, okay? So let's jump to the Amiga. I'm trying to, I will explain it, but just bear with me, believe the values that we have there, okay? So let's jump to the Amiga. Read the values, read the our example. Okay, remember FF00, 0F00, and C, but these are going to change, okay? Just to keep that in mind. A, X, K. The first one, okay, we did a not word on this memory location where data 1 is. So if we had FF00, this becomes 00FF. Okay, that's the first thing. The second one, we have 0F00. Because we're going to do a not on that one too, okay, it's going to come. This will become F0FF. So I'm going to execute it. And trust me, it has become as I said. And I'm going to show you that by going into the memory location 401 85 E46. It's the hex number. So 00FF and then F0 F0FF. Okay, those were our memory locations. So we did a negate there. Now we're going to move, okay, FF00 into the 0. So the 0 has the FF00, ignore what's in the high word right now. And we have the N flag set because the high bit is set of this one. The next instruction is an AND, okay, with data 1. Data 1 has got the value of 00FF. So 00FF on this word, okay, will produce a 0. Okay, so if we execute it, you can see we have a 0 in the low word because we are working on words. Okay, now we're going to do move 3 into the 0. Okay, always word. Okay, so you can see the 3 into the 0. Now we're going to do an AND with the value that is in data 2, which is F0FF. Hence, when we execute it, we get the value of 3. Okay, because only the bits, remember it's an AND, only the bits that are the same will be set, and we will end up with 3. So F0, FF, and 3 is 3, of course. Now we have 8,000 into the 0. So we have 8,000 to the 0. Now we're going to OR it. So OR it is normally setting bits, not switching, and this for switching bits off. OR is for setting bits on. Okay? You remember this from lesson, I think it's 4 or 5. Not 4, from chapter 4 or 5. I can't remember which one, but one of them. So once we execute the OR, okay, notice the N flag is set because it's an 8,000, but we end with 80FF. Okay, so far so good. Next one, we are moving 8,000 into the 0. Now we are going to do an XOR. Okay, so we're going to invert the bits with what is in data 3, and data 3 has got the value of C000. So when you invert the bit against those, if we execute it, you end up with a value in, because it's not in the, remember, the XOR was the 0 into a memory location. The value is in the memory location. The 0 doesn't change. Okay? The memory location 40185E4A will have, okay, a value of 0. We can test these, all of them now. We can do let's do 401, because I don't remember what was the start address. 401.85 E46. So we have the 0 FF of data 2, I think, and then we should have, okay, actually these are what we ended up. Okay, sorry. So the first one is data 1, which is 00FF. The second one is data 2, which is F0FF. And now data 3 should be 0. It's 40. Sorry, it's 40. So XOR of that is 40. We XORed 8,000 with CO00. So yes, actually it does make sense. It's 40. It's like the difference between both. So I believe this is, give me a second because I made a mess again on my desktop. This is number 3 or 4. 4 we did, I believe. Yeah, we did 4. So let's switch back to the book. One thing that I didn't mention is not this one. Patience with me. Yeah. So one thing that I didn't mention is that the move and TST, okay, the flags behave like the following. When the V and C flag are set to 0, the X is not modified, the Z flag is set to 1 if the result is 0, and the M flag is set to 1 if the high bit, whether it's a byte, a word or long word, is set to 1. So let's move to number 5. Sorry, we did 5, no? Number 6, I assume. No, we didn't do 5. We were in 4. I do apologize. This is the negate instruction. Okay. So basically we have values in data 1, 2, 3, and 4. Okay. And we are going to negate them. Okay. Change them. Okay. Into negative numbers or whatever. And you're going to see how the values are going to change and how things are going to be set. So we're going to negate what is in this memory location, which is FF02. That value will change to...
Listen!
Oh, sorry. I didn't switch to the Amiga. Sorry. Good job. Thanks, Hound Dog. You caught me exactly in time. So we have these negate instructions, okay, and they are going to work on these 4 memory locations with these values, okay. So this is another example that is hard to show because we are working on memory, but when we do negate data 1, the answer will be FE. The second one will be B0 FE, okay. The third one will be at 0, and the fourth one will be a number that will not fit, and hence we will have the X and VC flags set, okay. In the others we will have the X set and the C flag set. In data 2 we will have X set, C set, and N set. X and C are a reflection of each other in this case, okay. In data 3 we will have the Z flag set because minus 0, I mean, you cannot negate, you cannot do 0 and minus 0 are the same basically, okay. So it remains 0 and the Z flag is set because we have a 0 flag. The fourth one, okay, we have a signed number there, negating that it will not fit, okay. And because it will not fit, we get all the flags set. We're going to see it. XK. And as you can see, the X and C were set, as I said, in the first one. And the value that we have is 00FE. Then we execute the next instruction. And again, this time, because the number is higher than we negate 4F02, it becomes BOFE, and because of that the N flag is set. Besides, we have also the X and C set. The next one, we have a 0 in data 3. Data 3, I mean minus, negate minus is still 0, so we have the 0 flag set. And the last one, the number doesn't fit. We have an overflow, and hence there is no result. I can show them to you. Let's do 401, 401, 87, 85, 716. So the first one, as I said, will be 00FE. There you are. The second one, which is data 2, will be 0 B0 FE. The third one, dot 3, will not change, will be 0, 0, and dot 4 will not change because we have an overflow. So it doesn't touch the memory location. Hence, the negate instructions. That's how they work. Checking my notes to make sure that I said everything related to them. Please note that there's a negate instruction X, neg X, okay? This is for when you are working with binary coded decimal. Nothing else. Let's do example 6p. But first, let's jump to the book. Sorry, P6. This is what we are going to execute. And we are going to do additions, okay? How the conditional codes will work, or flex, will work when we are doing additions, okay? Remember, we get a carry. It's like normal maths, no? We get a carry when we have exceeded 10, okay? When we have 10 or more, we get a carry, and same with binary numbers. Let's see if I said everything in my notes before I jump there. So carry is set if the result is bigger, okay? Overflow is set if the number cannot fit. 0 is set if the result is 0. Negative is set if the result is if the high bit is set, and the extended bit is same as C. So let's do that. J, K, X, and K. So we executed the move.word, okay, into the 0, and we have the 4000. Now we're going to move 2000 into the 1, and we're going to add them together. And now we're going to add the 0 and the 1, so we should see the result in the 1, which is, of course, 2000 plus 4000 is 6000. Hence, we have the correct result. Now, we are going to make, we are going to deal with signed numbers, I believe, if I remember correctly. So, each 0 is signed, okay? It's a minus. So you see the negative flag set. We have also move.word B000, so that's also a negative number. So when we do K, we get a number that cannot fit. We have the negative flag set. Sorry, I haven't executed actually. Sorry. There you go. We have the negative flag set, the carry set. Of course, the X is a reflection of the, but the number doesn't fit in the current size that we have. Next one is two positive numbers, if I remember also correctly. So we have 6000, we moved it into the 0. We have 5000, which will move into the 1. You can see them there. Now we're going to add them together. So 5000 plus 6000, that is 11,000 or B000. Hence, because we are dealing with signed numbers, that the result is but it can be, it depends, okay? If we are dealing with signed numbers, then we have the overflow set. But if we are not dealing with signed numbers, then the result is fine. So it depends in which mode we are working. Hence, B00 for two positive numbers is correct. But if we were considering negative numbers, then that answer will not fit, because the maximum number that we can have in a word is 7FFF. As positive, I mean. Now we're going to deal with two negative numbers. So 9,000 is a negative number, and we moved it into the 0. We moved into the 1 also 8,000, A and 3 zeros. Okay, when we add them together, both of them are negative numbers, so the V flag is set and the carry is set. Even if we even if we treat them as two positive numbers, the number will not fit. So in either case, we need to deal with this in a separate way. Okay, either have our routine or something like that, or change the answer into a long. Okay, so that explains lesson 6. I'm just going to go through my notes, switch to the book. Okay, let's start again. X. Okay, we're going to move 2000 into the 1. We're going to move we move 4,000 into the 1. We move 2,000 into the 4,000 into the 0. Sorry, starting again from the beginning because I just got lost. So we're moving 4,000 into the 0. We're moving 2,000 into the 1. We're going to add them together. So 4,000 and 2,000 together is 6,000, and we should see 6,000 into the 1, which is correct. Now we are going to move a negative number, which is E0000, and another one, which is B000. Adding them together, okay, will give us the number does not fit, okay? Whether they are positive or negative numbers, no matter what they are, how they are treated. So the value doesn't fit, so we have a carry, and because we can be working on negative number, we have the N flag set. Now we're going to move 6,000 into the 0 and 5,000 into the 1. If they are positive numbers, when we add them, the result is correct. We have B000. But if we were working with signed numbers, then the answer is wrong, and hence the V flag is set and the M flag is set. Last one, we are moving A000 into A1 into the 1, and and 9,000 into the 0. I forgot to say that. So adding them together, okay, 9,000 plus A000, that will not fit in a word. Okay, so when we execute the instruction, we get the X and C set, of course, because they reflect each other, and the V, which is an overflow. And the answer doesn't, we have a 3,000, but in D1, but we know that is not correct because we need to add the carry to it. So be careful of this when you are doing such additions. So we arrived to lesson number 7. Let me read it. But first I'm going to jump to the book. So this one, okay, we have two numbers that we are moving into the 0 and the 1. We compare them, but we do a branch of greater than, so we do a jump depending on the result of the compare. But these two numbers, the 9,000 is signed and the 6,000 is not signed, is a plus. So this is a positive number, a negative number, and this is a positive number. So when we compare the 0 with the 1, I mean, of course, 6,000 is greater than a minus of 9,000, okay? Whatever that is, in 2's complement. Because of that, we will do the branch. Let's see it. We jump to the Amiga. Assemble X, K. So we moved the 9,000 into the 0. We are going to move the 6,000 into the 1. We are going to compare them. Look at the flags. Okay, we have X, N, V, and C set. Is the number bigger? It is. Hence, we do the jump. We went into no op, and I'm going to show you. If we didn't do the jump, we would have seen RTS. But we jump because this is bigger, okay? And we went into here where the no op is. We have arrived to where the Italian version finished yesterday. Okay, next week we will continue and finish P8 and P9. I can assure you, okay, P8 and P9 are a bit long, okay? So I do not know. I'm hoping that I will start Blitter next week, but I'm not 100% sure. Also, Fabio talks, and it's an interesting subject actually, how to insert data, which is graphics data, into your code. Okay, plus we will end up with a what you call it, a routine, not routine, actually it's actually a program which we will go into the detail of it, and I also will show you an enhanced version of it that I made, which I shared already with Patreon. Okay, they have all the source code for it, the Patreon guys that support me, and in it, okay, I have how to say, in it I have extended the program of Fabio, and in it I've managed to extend it so that it detects any type of Amiga that we are on, and we can know before we run something the type of hardware that we are going to run our software on. So let's say you are trying to run something which is AGA, but you are on an Amiga 500 which is OCS or ECS. Hence, it will not run. It will detect that. Okay, so that's what's going to happen next stream. In next stream. Thank you very much for being here. I appreciate all your support. Much appreciated. I hope to see you next week. Thank you and bye bye. See you next week. Bye. Bye bye.